This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Chapter 3 of Curious Math, Numbers that Change the World. Infinity, Beyond the Infinite. In this chapter, you'll learn: define the concept of infinity and its mathematical properties. Let's dive in. A computer once spent months calculating digits of pi and still didn't get all of them. Now pause on this. Someone else could start the same task, forever behind, and yet both would be chasing the same number. Today, we're diving into how infinity quietly breaks common sense. Cantor once showed that even if you listed numbers forever, you'd still miss most of them. That's not just abstract cleverness, it's a fracture line running through math, physics, and even computer science. The moment we let go of the idea that infinite just means very, very big, strange consequences follow. Some equations need infinitely many steps to make sense, yet give a clean, finite answer, like a perfectly tuned orchestra of terms, where adding infinitely many instruments somehow produces a single, exact note. This isn't just theory humming in the background. Engineers rely on infinite series to model signals on your phone. Algorithms lean on limits to keep graphics smooth and stable. And at the largest scale, cosmologists use these ideas to ask a wild, practical question. Does space go on without end, or does it quietly loop back on itself beyond what we can see? Cantor's work didn't just classify sizes of the infinite, it cracked open a hierarchy. There's the infinity of counting numbers, a larger infinity of real numbers, and then still higher tiers, like a ladder with no top rung. Mathematicians label these with symbols such as F0, Aleph null, and explore how they behave under arithmetic. What happens if you add or multiply infinite sizes? Meanwhile, physicists wrestle with infinities as errors. When quantum field theories spit out infinite values, they must be tamed or renormalized to match the finite world we measure. Think about how much structure hides inside endless. Start with Cantor's result that there's no one-to-one matching between natural numbers and real numbers. That proof doesn't just say, there's more stuff in et. It exposes a fault line in what it means to describe things with information. Take any scheme to encode each real number as an infinite string of digits. Cantor's diagonal trick guarantees a new real number that dodges every entry on your list. In information terms, most real numbers are algorithmically indescribable. No finite program, in any language, will ever spit them out digit by digit. They exist in the mathematics, yet can never be named, stored, or computed. Almost every point on the number line is, in this sense, forever beyond technology. This tension shows up in analysis too. The Basel sum 1 plus 1/4 plus 1/9 converging to pi squared over 6 isn't just a neat identity. It underlies Fourier analysis, where functions get decomposed into infinitely many frequency components. When your music app cleans up noise or compresses audio, it's exploiting the fact that infinite decompositions can often be approximated astonishingly well by truncating after finitely many terms. Infinity sets the theory. Finiteness pays the bills. On the computing side, algorithms constantly flirt with the infinite and then pull back at the last moment. Numerical methods for solving differential equations, simulating airflow over a wing, or training a neural network are all built to approximate ideals that live in infinite dimensional spaces. Yet they must commit to specific cutoffs: mesh sizes, step counts, precision limits. Every infinite object a computer touches is a shadow cast onto a finite grid. Even physics uses infinity as both a tool and a warning sign. Models of fields, waves, and spacetime are typically formulated on continuous backgrounds, saturated with uncountably many points. But any measurement we make, any detector click, pixel brightness, or voltage reading, is a finite summary of that continuum. Modern experiments press this boundary. Higher precision effectively asks nature, how long can you keep behaving like a smooth, infinite system before something granular shows through?
A chess engine doesn't see the whole game tree. It samples tiny, finite slices of a structure that, in principle, stretches without bound as you add move after move. That same dance between boundlessness and cutoffs shows up in technology everywhere.
Streaming platforms, for example, treat your endless listening history as if it were part of a vast function defined on all possible users. The recommendation model lives in a space so large that even giant data centers only ever skim a vanishingly small corner. Yet those partial glimpses are enough to make eerily sharp predictions. In medical imaging, MRI scanners reconstruct pictures of your body by collecting discrete measurements that stand in for data living on a continuum. Hardware can only grab finitely many samples in finite time, but the reconstruction algorithms are built as if there were an underlying, perfectly detailed object to approach. Your challenge this week: pick one everyday technology, maps, photos, music, GPS, and trace how it quietly leans on something unbounded, then is forced to cut it down to size. Infinity may stay out of reach, but how we choose to talk about it will shape future tools. Set theoretic choices, like accepting large cardinals, can ripple into proof assistants that certify hardware, cryptography, even AI safety arguments. Cosmology faces a similar fork. If observations keep favoring an endless cosmos, questions about typical observers and multiverses stop being philosophy and start constraining actual models of how rare or fragile our kind of universe is. Infinity keeps slipping past any fence we build for it. New algorithms test how far we can chase pi, while quantum theories hint that the continuum itself may be an approximation. Like a city whose map grows denser with every survey, our models expand, but the streets of the infinite always extend just beyond the latest edge of our chart. Start with this tiny habit. When you notice you're waiting, like in a line, for a video to load, or for the microwave to beep, quietly pick a number, say 7, and imagine Hilbert's Hotel trying to fit infinitely many new guests starting from that number. 7 moves to room 14, 8 to 16, etc. Just spend 10 seconds picturing the rooms stretching out forever and how everyone still finds a place. If you're sitting down, you can instead glance at any object near you and ask, how many times could I divide this in half in my imagination? And let your mind walk through 2 or 3 imaginary cuts. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!